Right. So again, welcome to this Virtual Time Series seminar. Our speaker is Leopoldo Catania from the University of Aarhus, and is talking about a new way to specify dynamic models. And the guest panelist who kindly agreed to be in is Genaro Sucarrat from Norwegian Business School. Right, so as usual, Leopoldo, you got 1 hour. I assume you're happy if people ask questions during the talk. Thank you.
Yeah.
And I mean, Genaro as well, of course, if you want. Recording will stop after the presentation, and then there will be question and answer if, still we have some. So Leopoldo, thanks very much, and the floor is yours.
Great. Thank you very much, Alessandra, for the invitation. I'm very happy to present in this seminar series. Now, this is very much work in progress, and also the title is probably going to change. So comments are very welcome. Yeah, please interrupt me during the presentation. At some point, there will be a lot of technical conditions and stuff like that. I will be fast on those parts because they are not really interesting. I would like more to give the message behind this paper. Now, the idea is that we often refer to this classification of dynamic models that has been proposed by Cox in a very influential paper. Essentially, he defines two classes of models, one called parameter-driven and the other one called observation-driven. Now, in the last 10 years or so, maybe slightly more, this classification has become more, let's say, discussed in the literature. That's because of the rise of a series of new observation-driven models that have been proposed according to this score-driven approach. And a lot of theory has been developed also for this observation-driven model. Parameter-driven models are models like state-space models. So we have like a signal, a noise, and then we would like to record the signal from a noise-contaminated version of it. Now, in my opinion, this classification, is very useful for pedagogical purposes. But sometimes it's a bit confusing. That's because to me it's easier to think of parameter-driven models and observation-driven models. As representation of a stochastic process. Now, the first part of the paper is actually focusing on this and providing an argument to move beyond this classification and try to have a look at them as representation of a stochastic process. Here is a very standard example. So, for example, here we have a very simple Gaussian signal plus noise model. So, can you see my mouse? I guess. So we have like a measurement equation and then a state equation. The state is an AR one. And then the measurement equation is the signal contaminated by a noise. Now, we do not observe alpha. We would like to infer about alpha by observing y. So we would like, for example, to compute moments of this alpha conditionally on some observations, some values for y. Starting from this representation of the model that we would say this model is parameter-driven, we can obtain another representation of the model, which is this second one in equation 2. And this second equation here arises by computing the Kalman filter and at the steady state. And this one would be called an observation-driven model. The idea is that now the variable of interest is this AT given t minus 1. And this one is now defined as an infinite combination of past y. And so in this second equation, yt is an observation-driven model. Now, if we compute the likelihood of the model starting from the first representation, the parameter-driven model, or the second representation, the observation-driven model, then the two likelihoods are exactly the same. So we would say that these two models are observationally equivalent. And so essentially, we are just representing stochastic process in a way which we might say parameter-driven, or in another way which we might say observation-driven. So what is the model for what is parameter-driven, observation-driven? I don't know. It depends on the representation. So some people in the literature, while dealing with observation-driven models, try to define objects which are typical of parameter-driven models, like filtered and smoothed estimates of the parameter of interest. And for example, if we have like an observation-driven model, some people try here to say, okay, what is the filtered or smoothed value of the parameter of interest now, which in the observation-driven model is this 80. And in my view, this question does not really make sense, because in an observation-driven model there is no filtered and there is no smoothed estimate of the variable of interest, because of the way the parameter, the model is defined. So now I'm gonna refer to parameter-driven and observation-driven specification. So general case for a parameter-driven specification is this one. Now we have our measurement and transition equation, and we have some IID shocks. And as a result of this specification of the model, what we obtain immediately is the measurement or emission density. So if we condition on alpha t, m is a known deterministic function. Knowing the law of epsilon, we recover the law of yt given alpha t. And then we also have the transition density available immediately by the specification of this transition equation. Now, in practice, what we would like to recover from this model is the state predictive density. So we would like to make prediction about the state variable using all past y, what y are observed. Then the state filtered density and the state smoothed density. So we would like to make inference based on current observation and future observations on the state variable. So these are objects of interest. And then, for example, to make predictions or for model estimation, if we would like to construct a likelihood function, then we are interested in this prediction density. Now, when we move from this linear Gaussian model, all these densities here are generally not available in closed form, depending on how complicated the model is. Evaluating these densities might get quite tricky. Now, in an observation-driven specification, what we have is a measurement equation, which I write in this way, and then we have a recursion of this kind for AT, and now for AT, and now AT is the variable, is the parameter of interest. Now, as a result of the model specification, of course, I'm assuming existence and a lot of regularity conditions behind this model. As a result of this model specification, what we have is the prediction density, and so this is immediately available. And so a likelihood can be constructed quite easily. Now, we don't have any filtered or smoothed value of this quantity here, simply because once we condition on all past y, then AT plus 1 given t is just deterministic. Okay, now in this paper, I consider an alternative model specification, which is something I refer to as extended observation-driven. Now, in this specification, we have a measurement equation as before, and now we have a state equation like in the parameter-driven specification. And now this state equation is driven by another shock, eta. And then we have a recursion for this a t plus 1 given t. And this is like the observation-driven case we had before. Now, you might ask me, why do we care about this? Why should we include this variable here, this extra equation here? The answer to this question is twofold. The first one is that by writing a model in this way, we will be able to develop new models, and we will be able to obtain new specifications that might be interesting for actual applications. And the second reason is that, as I will show you later, it is possible to obtain an extended observation-driven representation of usual observation-driven models. And this representation is going to provide is going to be more insightful. So it's going to be more interesting, in my view, to understand the structure of the observation-driven model we started from. I'm going to be more clear on this point later. Now, if we write down a model in this way as an extended observation-driven specification, then the measurement or emission density is again available immediately. So because we condition on alpha t, then epsilon t, we know the law of epsilon t, m is a non-deterministic function, so yt given alpha t is immediately available. And the state predictive density is also immediately available. That's because if we condition on all past y, I'm skipping a lot of regularity conditions that will be reported later, of course. But if we condition on all past y, then this at given, let's say, t minus 1 is known, eta is known, g is a known function, and so we obtain the distribution of alpha t given all past yt immediately. So this is what we would call state predictive density in a parameter-driven representation. So the model really specifies these two distributions here. And then what we would like to recover is the prediction density. So for example, if we want to construct a likelihood function, and this is available after by solving this integral here. Note that this is one integral. It's not like in parameter-driven specifications where we need to integrate out all past state variables. Here we only need to integrate out this alpha t. And many times this integral is available in closed form. And then the state filtered density is also immediately available by a simple application of Bayes' rule. So it can be easily computed. And then it can be shown that for a model like this one, for an extended observation-driven model, the state smoothed and the state filtered densities coincide. So this is a bit counterintuitive, but it's really a result of the model specification. Okay, a nice feature about setting up an extended observation-driven model is that we immediately obtain an observation-driven representation of the model. This is quite straightforward because we start from here. And then what we can do is simply take this equation here and put it here. And now rewrite the equation as a function of a new shock, which is a function of epsilon t and eta t. Epsilon t and eta t are both IID, so this new shock is going to be IID as well. And this is simply the observation-driven representation of this EOD model. And then what we can also obtain is a quote parameter-driven representation. Now I will discuss about the quotes here. And this is obtained by playing, as before, with the model specification. So we have a measurement equation, and then we have a state equation. The quote part here comes from the fact that now these shocks in the transition equation of this PD representation is not IID anymore. So, and you can see it's not IID because it's defined in this way. So this is not really a parameter-driven representation of the model, is something similar to it. However, it's completely legit, so we can rely on it. Now, some examples. Here there is one example, a quote stochastic volatility model. So we have our measurement equation here. And then we simply assume, for example, that alpha t, the state variable, is defined in this way. And then we set up a recursion for this AT given t minus 1. And now here I define something like this out of simplicity. But of course, different specifications can be set up. Now, the quote parameter-driven representation of the model is given by this expression here. So you see that now the state variable is defined as a function of past and present shocks. Whereas the observation-driven representation is something which looks like a Nigarch model, kind of. Where now the shocks here are is a function of this eta t and this epsilon t. So it's effectively omega t, wt is equal to x of eta t divided by 2 times epsilon t, and it has the name of the associated density is the normal log normal density. Okay, so it has a name. So we can start from the model in 5. We can perform model estimation by maximum likelihood by resorting to the representation in 7. We can compute filtered or predictive densities of the state variable alpha t using the formulas I showed you before. Also, we can easily construct confidence intervals around point estimates of the state variable, like we do in parameter-driven models, well, like we usually do in parameter-driven models. And I have an example later regarding this. Here is another example, which is not really, I'm going to skip, it's just signal plus noise. I would like to show you this third example here. And this is another application of this, let's call it methodology. So what we can do, we can start from an observation-driven model, like the T-Garch, a simple Garch model with T-shocks. And then what we can obtain is a possible extended observation-driven representation of the model. This is one of many, of course. So when we go from an observation-driven model to an extended observation-driven model, the map is not unique, so we can find many. So if we exploit the stochastic representation of a student T random variable as a scale mixture of a Gaussian scale mixture where the scaling variable is a scale inverse chi-square, what we can do is to simply rewrite equation 12, so this observation-driven model in this way. Now we have a measurement equation, and in this measurement equation we have a state variable and some shocks, and these shocks are Gaussian in this representation here. And then we have a state variable, alpha t, and this is its specification. And now the shocks in the state variable are scale inverse chi-square. And this AT given T minus 1 follows the usual Garch recursion here. Now, this allows us to, so now I parameterize this scale inverse chi-square distribution such that its expectation is 1. And so we can compute the expectation of alpha t given past y's, and it's simply going to be this one. But we can also compute the variance of alpha t given past y, and it's going to be a function of the variance of eta t. Besides being able to fully characterize the predictive distribution of the state variable, we can also obtain an alternative stochastic recurrence equation for, in this case, the volatility. For example, so here in this model, we have that the state predictive density is a scale inverse chi-square. And the state filtered density is also scaled inverse chi-square. So here, this is a result of the conjugacy of the scale inverse chi-square with the Gaussian distribution. And so we have these distributions. We can compute everything. So, for example, the predictive mean, the filtered mean, predictive variance, and filtered variance of the state variable. Also playing with this filtered and predictive mean of the state variable, we obtain a recursion for the volatility. Now the conditional volatility evolves in this way. So this is exactly the same as before. So if you run this filter from the same starting point in this way, or using the common Garch recursion, you obtain exactly the same values. However, now this volatility recursion here is expressed in terms of filtered and predictive estimates, and this closely resembles what we have, for example, in the Kalman filter. So in the Kalman filter, this term would not be there. We would only have these filtered estimates. And this can be obtained if under some conditions on this k parameter here, which is the one associated to the square returns in the usual Garch recursion. So by setting up an extended observation-driven representation, we were able to just represent this usual Garch recursion, which involves an arbitrary transformation of the observed variables y square. We use it, it does make sense. But we can now represent the model using filtered and predictive estimates like we do in state-space models, like with the Kalman filter, and this makes much more sense to me, at least. Now, I will show you later that this way of writing the recursion for this parameter here, alpha t plus 1 given t, in terms of filtered and predictive estimates, allow us to gain interpretability of, for example, score-driven models when we set up a score-driven models for a location or for a dynamic location or a dynamic scale. Yeah, here we are. So recently, not so recently nowadays, but yeah, some years ago, this approach called score-driven models has been proposed by Kriel, Kopman, and Lucas, and by Andrew Harvey. Now they call it, so the Amsterdam crew call it GAS, Generalized Autoregressive Score. Andrew called it Dynamic Conditional Score. Nowadays, we call it score-driven. So this is, we are converged to score-driven. So this is a subclass of observation-driven models. And now the idea is to set up a model like this one, so an observation-driven model, where now the forcing variable of this stochastic recurrence equation is defined as a function of the score of the predictive distribution implied by the model. So by writing the model in this way, we immediately have we have the, under existence of the model, of course, we have this density immediately available. What we do is we compute the score, and then this is this nullity. Then we also define another object, ST. This is simply a positive quantity. And then we define the forcing variable in this way. Now, the idea is that in Garch, we use yt square. Why do we use yt square? Well, let's use something else. And this something else is a function of y still. Okay, now this ST is a scaling term. Sometimes is set up as a function of the information quantity. So for example, if we set this d equal to -1/2, then this ut is a unit variance marking a different sequence. But sometimes evaluating this quantity is complicated, so we just set e equal to 0. So the literature is, I mean, there are some results about how to choose ST and also specifically how to choose D sometimes based on some optimality criteria. However, in practice, people set ST in a way such that the model is manageable. So there is no real agreement so far in the literature about how to specify ST. I have an example later where after putting this an observation-driven models of this kind in an extended observation-driven specification, we might have some guidance about how to choose ST. I will comment on this later. Now I will now comment on two possible specifications of score-driven models. One is a state, what I call a score-driven state location extended observation-driven model. Now, in a model like this one, we have our measurement equation here. And now the state variable follows is defined in this way. And now this is the time varying parameter. And what we would like to do is set up a score-driven recursion for the dynamic parameter. And for simplicity, I'm simply gonna set this d equal to 0, so unit scaling. So the forcing variable is just the score. Now, if we compute the score in this setup, we obtain this formula here. So we see that the score is actually filtered estimate of the score of the state variable. Now this is still a bit cryptic, so it's something, but it's not I mean completely clear what's going on. So let's make another example. Now suppose that the shocks, where am I? Suppose that the shocks in the state equation here are Gaussian. So suppose that this eta t here is Gaussian. So this is the density. And now we have that the predictive estimate of the state variable is simply given by AT given t minus 1. So this is under the assumption that assume this is standard Gaussian for simplicity. Now the score looks like, well, it's not, there is this tau, it's not standard Gaussian, there is this tau. So now the score looks like this, the score of the state variable. And if we compute, for example, tau squared times this nullity, what we obtain is that the UT variable, so the score we would use to update the dynamic parameter, is simply the difference between the filtered and predictive estimate of the state variable. And this is exactly what's going on in a Kalman filter. And so we can rewrite well, we can rewrite this expression here, this recursion here, by replacing UT with what we just found. And we obtain that in a score-driven model that has been set up in an extended observation-driven way, where the shocks of the state variable are Gaussian, we obtain a recursion which again resembles the one of the Kalman filter. And specifically, when phi is equal to this kappa tilde, which is simply a function of the parameters of the model, then we obtain exactly what we would have in the Kalman filter. And to me, this is it's quite interesting, because now for a very general class of model specification like this one, where I was not so specific about this. So this is general. As long as we assume these shocks to be Gaussian and we rely on the score-driven approach to obtain a recursion for AT, then we obtain something which is like the Kalman filter, something we are very much used to. Okay, what about state scale model? Now, here we still have our measurement equation like before, but now the state variable is not defined as in the additive way as before, but now it has this multiplicative form. And again, we have some IID shocks. If we do exactly the same as before and we compute the score, then we obtain this expression here. This is still a filtered estimate of transformation of the shock in the state equation. So it's something, it's not super intuitive. So let's have a look for specific choices of eta t. For example, let's focus on this beta T Garch model. So this is a model proposed by Andrew Harvey and Chakravarti in 2008. Is one of the very first score-driven models. The idea is to generalize the Garch model. And now the model is defined in this way, where this term here, so the forcing variable, is the score scaled by this quantity here. The idea behind these models is that when the degrees of freedom of the shocks Wt goes to infinity, then this Wt becomes Gaussian. And then actually equation 22 resembles the standard Garch recursion. However, when the degrees of freedom parameters is finite, then this quantity here is bounded almost surely. And so even if we observe very large realizations of YT, which are usually financial returns that can be very crazy sometimes, then the response of the volatility, of the conditional volatility to these very large returns is bounded. So this is why we would like to estimate a model like this one. Okay, now what we can do is to again exploit the stochastic representation of Wt in terms of a scale inverse chi-square and a Gaussian distribution. and write an extended observation-driven model and see what's going on behind this specification here, because I mean this is indeed appealing. So okay, if nu is finite, then this is bounded. But I mean it seems a bit ad hoc. So what's behind this? What's behind this updating mechanism? Okay, let's do that. So we just rewrite the model in this way, as I did before for the T-Garch. And then after a bit of algebra, and by exploiting the properties of the scale inverse chi-square. So again, in this specification of the model, I can easily compute the predicted and filtered densities of alpha t. And these are going to be scale inverse chi-square, exactly as before. And now playing with the properties of the scale, with the scale inverse chi-square, we obtain the filtered mean of alpha t. And what we can do is to represent the beta T-Garch recursion as a function of the filtered and the predicted mean of the state variable. And this is, to me, much more interesting than having this transformation of yt, because it still resembles what we have in the Kalman filter. So we compute predictive estimates of the state variable while looking at the last filtered estimate and the previous predictive estimate of the state variable. Now, this result relies on the choice made in this paper by scaling the score by this quantity, which is proportional to the information quantity. Now, if we choose a different scaling mechanism, so if instead of choosing this inverse scaling, so d equal -1 in the notation I used before, we use this inverse square root scaling. Now we say that d is equal to -1/2. Yeah, here there is a typo. Okay, so but if we do this, then instead of obtaining the recursion we obtained before, we obtain this other recursion, which is also very intuitive to me and a bit more intuitive than before. That's because it is, I mean, it's similar to what's going on in a Kalman filter, but now instead of having the difference between filtered and predictive mean of the state variable, we have the ratio. And so this is telling us how to update the time varying parameter or the predictive mean of the state variable. Okay, now I'm gonna be fast here. First of all, because I'm still working on this part, and also because there are a lot of formulas and it is very boring. Now, in the paper, what I do is I consider this general specification, and what I do is I propose to estimate the model by the MLE resorting to the observation-driven representation of the model. And then I provide limiting results for the MLE and conditions on the existence of solution for a stationary ergodic solution for this model. So I have some regularity conditions on so I have many things to control because there are these m, g, and psi functions, and then I have the law of epsilon and eta. And so I need regularity conditions on all these things. Specifically, I need some conditions on derivatives of all these functions and existence of the inverses of all these functions and derivatives of the inverses of all these functions, plus some moment conditions. And this, for those of you that work with observation-driven models, this might be quite familiar. So these are simply conditions to establish the existence of a unique strictly stationary ergodic solution for the YT process, so from which we observe trajectories, and then the state variables, and also the time varying parameter AT given t minus 1. And then we can define the MLE in this way, and we face the usual issues that we do not observe the value of the time varying parameter at time 1 or at time 0, depending when you want to start the recursion. And so what we do for each choice of theta, then we select some starting values, and then we will like, and then we construct a likelihood function based on this initialized recursion. And now the idea is that we want to assure that the difference between the stationary and ergodic likelihood function and the one initialized at our arbitrary point goes to 0 almost surely. And so we can do that. So this is what we can compute in practice. And then we have some other regularity conditions. And then we have an invertibility result. So provided that these other conditions hold, which involves logarithmic moments of derivatives of the filter, then we have this exponentially fast, almost sure convergence to 0 of the difference between the initialized sequence and the stationary ergodic sequence uniformly over the parameter space. Now, this result allows us then to easily show after the assumption after some other technical assumption, to easily show the almost sure convergence to 0 of the difference between the stationary ergodic likelihood function and its empirical version. Then we need some conditions for identification. Specifically these two conditions. Now I'm going to use this notation. Now, essentially what we have is that the predictive density of YT is a continuous mixture because when we compute it, we integrate over alpha t. And what we have is that we need some identification condition on it. So, for example, we need conditions of this kind, which, given specific choices of all the ingredients of the model, can be checked exploiting this theorem in this paper. And then this second condition here. It's pretty standard in the literature, and if we employ stochastic specific choice for psi t, so the stochastic map of AT, then this assumption can be checked quite easily. And now after another moment condition of this kind, we obtain the strong consistency of the MLE, of the feasible MLE. Okay, and now I'm gonna skip this. We have some other technical conditions. And after many technical conditions, we can obtain I mean, the asymptotic normality of the MLE, and I mean, we can use it to perform inference. Then in the paper, I also provide an example of this methodology, and the idea here is to provide an analog of what the beta T gauge does in the volatility context to the duration in the duration framework. So in the duration framework, we have this exponential autoregressive conditional duration model. So this model is used, for example, to predict the time between the execution of two trades and stuff like that. And I mean, it's like a gauge. It's really like a gauge. Now, what we can do is to set up a model like this one, where again, I have some exponential shocks, standard exponential shocks, a state variable, and then I have this multiplicative form. And then I have some other shocks in the state equation, which are assumed to be inverse Gaussian. And now if we use the if you use the score approach to compute this forcing variable ut, then we obtain nice results as those I showed you before. However, the nice feature of this specification here is that when the degrees of freedom, I mean the shape parameters here of this inverse Gaussian distribution diverge, then we actually obtain the exponential autoregressive conditional duration model. So this model here generalizes the model by Engel and Russell in the same way as the beta T gauge model of Harvey and Chakravarti generalizes the gauge model. And yeah, so if we set ut proportional to the score, then we obtain this. This is the score, and now it's defined as a function of zt. So this is what we would have. We would have in a observation-driven specification. However, we can exploit the properties of the scale inverse chi-square, of the inverse Gaussian distribution, sorry, we used before, and obtain again filtered and predictive estimates of the state variable, and again compute all quantities of interest of the model. So, for example, predicted mean of the state variable, which in this case coincide with the predictive mean of the observables, but also filtered mean of the state variable. Now, exploiting these two results, so this expression for the filtered estimates and this expression for the predictive estimates, I don't have an example, but we can rewrite this recursion as a function again of filtered and predictive estimates of the state variable, which to me is quite cool. And then I have some results about existence of a solution. Here we have something very similar to the condition we have in a gauge model for strict stationarity. And then we have conditions for weak conditions for existence of the mean and conditions for existence of the variance. Note that as in gauge, we can have a model which is yeah, I mean, we have the same issue about weak and strong stationarity. And then we can compute predictions quite easily. So everything here is available in closed form. And this is the response of this 80 plus 1 given t to a new value of yt. And you see that when this new parameters is equal to infinity, then the response is linear, and this is the exponential autoregressive conditional duration model of Engel and Russell. But when the degrees of when this parameter mu t is finite, then we obtain this bounded response, exactly the same that happens in the beta t Garch model. Okay, I think I'm close to the conclusion because now this is my illustration, which is made of two figures. So the idea is that you estimate a beta t Garch model because it's robust to extreme observations and generalized Garch and everything. And what you are left with is this black line. So this is the volatility, the predicted volatility from the beta t Garch model. Now, if you cast the beta t Garch model in an extended observation driven representation, then the black line becomes the expected value of the state variable given past y. But since you know the distribution of alpha t given past y, then you can easily compute quantiles. And so you can easily attach confidence bands to these predictive estimates. And now you have a coherent way to attach confidence bands to what you might call an observation-driven model. So you start from an observation-driven models. By the way you define the model, you don't have any confidence bands. However, you can cast it in an extended observation-driven representation. And now the black line is going to be exactly the same, but you can attach confidence bands. Furthermore, you can compute filtered estimates. And since you have the whole filtered distribution of the state variable, you can compute its mean and its quantiles. And so you can have confidence bands attached to the filtered mean. So what is in this paper? There's a new way to specify dynamic models. There are results for the Emily. The message that observation-driven models can be put in extended observation-driven form and gain interpretability by, after this process. And then you can construct filtered and predictive estimates with confidence bands in a statistically coherent way. What I would like to work on is to relax some assumptions I made. So in the parts where I was fast, I made some, I had some conditions that were involving taking a soup over the space of the time varying parameter, and this can be quite restrictive sometimes. And then I'm working on some primitive conditions for these exponential observation-driven models and maybe an empirical analysis. So this concludes the presentation.
Thank you very much, Leopoldo. Let me stop the recording. Right.